Welcome to today's webinar with the title Fan out of a BGA pitch 0.35 millimeters. This is how it works. I am Andreas Schilb, your host of today's Würth Elektronik Circuit Board Technology webinar, and I would like to welcome you. The speakers in today's webinar are two experienced specialists from Würth Elektronik Circuit Board Technology, Michael Kress, Head of the Technical Project Management, and Michael Mattes, Specialist for Layout and Measurement Technology, and therefore Head of our service VF-BGA. Welcome, Michael and Michael. And I wish you lots of fun and new information.
But now it's our turn. Okay, Andreas, thanks a lot for the short introduction of us two, and also greetings to Bengaluru. Maybe that are colleagues from us in the company over there. Now let's have a close look to the agenda. At first we see the development flow from the point of view of the designer, of a developer. There was some information about specification and requirements for the assembly, the component selection and study of data sheets is a point we need to discuss, and the clarification of parameters of the PCB manufacturer are needed for the developer, for the designer to do a good job. Now it's up to you.
So, thank you, Michael. In the middle of the presentation, I will show you what is possible and what is not possible of the PCB manufacturing. So where's the parameters and where are the less parameters of this recommendation from the PCB manufacturer, the impedance for the build-up, and at last the reliability of PCBs.
Okay, and the third part of the presentation is the implementation in the design. How are the impedance modules are set up? What is the stack up of the whole construction? And we have a close look to the design itself. So let's start with the specification. At first, we need to create the specification based on the requirements for the construction, for the assembling, power or environmental requirements, other information such as mounting positions, locations, what is the situation, maybe also part specifications are part of the requirements. When you are going to select components, the requirements must be taken in account. It can be information about thermal parameters, mechanical, lifetime as MTBF parameters, such things. You have to take care on. After the components are selected, you need to set them up in the library, the component library for your EDA tool. And the third step is to create the circuit diagram, the schematic itself, and you need also to fill in constraints, rule sets such as track widths, differential pairs, amperes, voltage, distances, such things. You need to put in, and at the end you need to talk to your PCB manufacturer to clarify all the open points. How is the layer structure? What is the material? What parameters do you offer for that materials? What are the impedance modules you need to use? Are there other requirements? So while choosing the components, or after choosing them, you need to study the data sheet. What are the general parameters? Is that part, or does that part fit for your product? There are information about blocking capacitors, such things, how you should develop the schematic. and also detailed information, which pin or which port does need that blocking information, that blocking capacitors. After setting up the schematic for the part, you need to set up the footprint. There are different libraries that are online available where you can download information, but please take care, because there are often false mistakes in that free library, so you need to check them if you are going to import them into your local database. Beneath the parameters like MTBF, thermal parameters, you have also the mechanical parameters that are, for example, the footprint or the dimension of the part itself. While setting up the footprint, you need to take care of special information. For example, the diameter of the ball, of the BGA ball itself. In this case, we have a diameter of 245 microns, or also the pitch. And in this case, we have 350 microns pitch. In the next step, I did a small picture. I developed a picture how the standard parameters are, and if you can realize them. So you can see the pitch with 350 microns. You see also the pad diameter with 240 microns. And here you see the solder mask, which is 50 microns bigger than the pad itself. So that's 100 microns on both sides. And if you are going to realize or set up the footprint with that parameters, you have a very, very small solder resist bridge of 10 microns, and that's not possible to realize in the PCB manufacturing. If you are going to route a track between the two pads, you have a line space distance from only 36.7 microns. It's also not realizable in the PCB production. And also there are some small parts of the tracks which are without solder mask, so maybe there is solder bridge after the assembling of that board. The BGA has several rows of pins, and if you are going to do the routing and you need to do the fan out from the inner rows, you need up to 3 or 4 traces between the pads. And if you don't change the layer by wires, you have an minimum line space information from 15.7 microns between the two pads and the 4 traces. So as designer, you need to ask yourself what are the options for realization, or better is to ask your PCB manufacturer. So it's up to you, Michael, to go on in the presentation.
Yeah, thank you, Michael. So at first, I will show you the standard parameters. So here you see standard microvias, pad size 300 microns, or for through-hole wires, pad size 550 microns. And all these parameters are good for 0.5 BGA components. And if you will use a smaller BGA component, perhaps from 4 or 0.4 millimeters, so you must reduce these parameters. And for example, I will give you information for pad diameter reducing with 25 microns. So for pad, for BGA component with 0.4 millimeter, it's not possible to use a pad diameter from 300 micron. Here you will reduce this to 275 or 250 perhaps. Very important for you, the solder mask requirements are very so they are fixed, and in the follow, I will show you a lot of parameters about this one. So at first, we make a calculation for this one. The biggest limit is our solder mask. Why is this? So the solder mask width is 70 microns. The clearance from the pad is 35 microns, and this is parameters, so there's fixed. So we will look to the right side. So we have a calculation about this one. So if we have pad to pad, we need minimum 140 microns. Why? The clearance on both sides, we need 35 microns. And the solder mask bridge mask web is 70 microns. And this is a fix from 140 microns. Plus the pad size, perhaps 275 microns. So we get in summary pitch from 415 microns. So now for pitch from 0.4 millimeter, we must look what we can reduce. So we can reduce the pad size to 250, 260 microns perhaps. And the next step is for pitch 0.35 millimeters, 350 microns. So only what we can do is to reduce the pad size of 210 microns. So, but we can only reduce the footprint pad sizes, but the solder mask is fixed. So the standard solder mask clearance is in advance 35 microns, the coverage 40 microns, and the solder mask web is 70 microns for standard PCBs. So very important for you. By standard PCBs, we have on the outer layer a copper thickness from 45 up to 55 microns copper thickness plus solder mask. So we get a solder mask thickness from 70 microns. And so the solder mask bridge must be used with 70 microns. What we can do for the BGA 0.35 millimeter, the recommendation to reduce the parameters for solder pad diameter. And we reduce this to a parameter from 215 microns. And in this pad, we will use a microwire pad directly in the pad with a copper filled process. So we have a very flat solder pad on the PCB. As a consequence, the PCB for this is that we use very thin electrical spacings. The PCB becomes very thin materials. So here we can use the very small microwires for the small pad. And here the calculation for this one, I will show you the calculation for the BGA pitch 0.3 is 250 microns component pad plus 2 solder mask clearance with 35 microns plus a solder mask web with 65 microns. So we have in summary a 3.5 millimeter BGA component pitch for this one. And so this is the parameters what we can go in the PCB design to produce this. So in the next here you can see the buildup, and you can see the very thin materials. In the core, the maximum core thickness is 0.1 millimeter thickness. This is the thickest core if we can use for laser drilled microwire. So we can use 50 microns, 60 microns, 100 microns cores. And for the prepreg to the outside, we can use 30 microns, 50 microns, maximum is 65 microns prepregs. And so the buildup from the complete PCB is very thin, maximum 0.35 millimeter up to 0.45 millimeter material thickness from the PCB. Furthermore, is to dispense the mechanical drilled microwires, connection because all of the copper structure to be limited to a maximum of 30 micron copper thickness. So very important. This is good for the design. So here you can use 75 microns isolations and width for the design. For me, very important to say is please don't use plated mechanical drilled through-hole wires. Why? So for the plated through-hole wires with mechanical drilling, we need minimum 20 up to 25 microns copper in the hole, and so the outer layer thickness go thicker and thicker. So for only use copper-filled microvias, we are the end copper thickness on the outer layer by 30-35 microns. If you use through-hole wires, so the end copper thickness on the outer layer, top and bottom layer, is 45 up to 55 microns. And so you can use the 75 microns line and width. On the next page, I will show you the impedance structure. In all considerations of the impedance, it must be said that the reference layer is the next layer is very thin, and so this is a problem for the impedance calculation. So here is to say that you every time to use the next layer as the reference layer. So if the distance are too small, the target impedance cannot reach by the old version. So in the reference layer is defined directly under the signal position, then the target impedance is reduced by 30 up to 50%. And so it's very important that the signal layer and the reference layer have a distance from 80 up to 100 microns, the electrical distance. And then you have normal calculation for impedance for single-ended 50 ohm or differential pairs for 90 ohms up to 100 ohms about this one. So very important. Signal layer perhaps top, and the reference layer is not a next inner layer, so we go to the layer 3. And what I will tell you, what is very, very good for this one, if we show and learn in the qualification that the PCB, the buildup is very thin, so we get very stiff PCBs. We make a test with these PCBs by reflow. Before we try them by 4 hours, 120 degrees. Then we soldered them by peak to 160 degrees, 6 repetitions about this one. And after them, we go in a shock test, terminal shock test by minus 555 degrees and up to 150 degrees by up to 500 cycles. We don't see every time about problems with the connections or other things. So we can say the PCB thickness is very thin, and this is very good for this one. Okay, so then we have all parameters for the design, and Michael can show you if they can work within these new designs.
Okay, Michael, thank you for that information. Now I'm the layouter, the designer, you are the PCB manufacturer, okay?
Okay.
And now I need that information provided by you at first to put them into my design setup in the footprint setup. And here see what are the modified information for setting up the footprint. And first we need to reduce the pad size from, I think the standard was 245. We reduce that to 215. We reduce the solder residue from 50 microns to 35 microns. We use wire in pad, that's allowed now. And we can achieve, or we need to use line space information or distances from 75 to 75 microns. But you need to take care on that information, because you should know about the processes, because the component manufacturer recommends you parameters, and now we deviate from them, and so you need to be sure that the process, the soldering process, the assembling process, and the subsequent processes are not influenced by that modification of not the stack up, but the footprint. Okay, now we have a short view on the impedance controlled traces. In order to calculate the impedance parameters, the edging angle of the tracks should be known. Normally you have a foot and a head of the single trace, of the single track. And you need to put that information into your EDA tool, into the constraints. But what information, what parameter do you enter in the tool? That's the question here at this point. The answer is that you fill in the width of the foot. That's 200 microns in this example, because with the foot you can also do optical inspection with the camera system, if you have the right value or if you don't achieve the right value. Now we have a small look on a 50 ohm single-ended RF antenna feed line. The component we've chosen has also an Bluetooth transceiver for 2.4 gigahertz on board, and for that you need, for example, for the antenna connector, that 50 ohm single-ended line on the PCB. Here we have a look at that realized track without solder mask and also with solder mask. And with these pictures I want to show you that you have a difference of nearly 5 ohms in that area if you are going to cover the copper area with solder mask. So you need to know that information. You need to use that information in your stack up, in your constraint set for that certain lines, for that certain tracks, that you have the right value you need, and you have to tune it to the right value. Here we have a look at the 90 ohm differential pairs. I think Michael told us something about 100 ohms differential, but we have also 90 ohm differential pairs. So here you have an example that's we compare two different tools here. They have nearly the same value, both around 90-91 ohms differential resistance. And if you want to have that parameter, you need to put in the calculated values of 135 microns per track. The spacing will be 75 microns here. If you have the 135 microns at the base, at the foot of the trace, you have 125 at the head. In order to get an edging compensation, the CAM of the PCB manufacturer is adding approximately 30 microns. Thus, you have 165 microns that are set in the photoresist, but that is done by the CAM of the PCB manufacturer, not by the designer. Here we have a view on the stack up in the EDA tool Allegro OrCAD from Cadence. You have all the parameters, the Z-axis information, the thicknesses of the copper foil, of the pre-breaks of the core, and also the dielectric parameters epsilon r for solder mask for the different materials you use in that stack up. Ideally, you can download that information directly from the PCB manufacturer's homepage and can import it in your tool, so you don't have to set that up in the tool manually. The stretchy of the stack up are copper-filled microvias, and so you have the possibility to stagger them or to stack them directly over each other. Here we have a demo placement of that component of the BGA with 350 microns pitch. In the upper area, you see the 90 ohm impedance, the differential lines. And on the right side, on the bottom, there's the antenna structure, the 50 ohm single-ended without solder mask. If you need to do the fan out from the inner rows, we have talked about the line width, the spacing. You cannot route between two pads of the outer BGA pad. So you need to change the layer of the PCB. So you go from the top layer to the layer 2, and then you need to take care what the reference layer is. So the lines, the differential pairs on the top layer have layer 3 as the reference layer, and if you change the layer to layer 2 as routing layer, you need to change, for example, the reference layer and need to go to the bottom layer as reference, or you can tune the line space information that you have the same impedance in that area you are in the layer 2 while routing. Here we have an overview of 3 different impedance modules. On the left side, you see the original 90 ohm with the routing layer top and the reference layer on layer 3. If you change from layer top to the layer 2 and leave the layer 3 at reference layer, the impedance is going to nearly 82 ohms, so you have a difference of nearly 10% in the impedance. If you're going to change the reference to layer 4, to the bottom layer, you have again the 130 microns distance, but you have a lot of material above the copper structure, so the impedance is also changing a little bit. Not that much as if you have another distance, but you have also an tolerance of 2 ohm in the impedance. Here you see the stack up, the single layers on the right side of that board, and you can see the gap, the cut out on layer 2. That is to have that distance to the reference layer that should not be influenced by the layer 2, and the reference layer at this construction is layer 3. And as I told you before, you have 2 possibilities. You can do it like this, that you have cutouts in the second layer, in the layer 2, or if you have that layer change with your routing information with the differential pair that is routed on the layer 2, you need to cut out the layer 3, the plane here also, to have layer 4, the bottom layer, as reference layer. The last picture in the presentation is this 3-dimensional view of that construction. You can see the BGA component, some capacitors and resistors around that. Here the differential pairs on the top layer. Also you can see the stacked microvias in that construction, and here are the the rooted differential pairs on layer 2.